Thanks very much for joining us. So today what we're going to do is continue on with our conversation about thermodynamics. Remember last time we started in on the introduction to thermodynamics. Does anybody remember generally if we sort of categorize what we are studying? If I give the name thermodynamics, what are we kind of getting at here? Heat, yeah. Changes in heat, that's right. It's moving around energy, and it's a focus on moving energy into and out of something. We defined sort of a language or a couple definitions to help us study this. So heat is one part, changes, yeah, we have a system. What else? There's one other part of the equation that matters too. There is system, and outside the system is the surroundings, right? We also said there were kinds of systems. What were they? We broke them into three categories. Yeah, boundary, that's a good point. Boundaries of the division. Yep. Open, right? Closed, isolated. Now, remember, there's a couple of specific definitions. Does anyone remember which of those three would you consider the most impossible? The one that we would never see a real world version of it? Yeah, isolated systems are kind of the perfect case. Now, what makes an isolated system special? What makes it different than the other ones specifically? Yeah, no energy can move. System can't lose energy or gain energy. No mass can move, right? So we have those two characterizations. Mass can either leave or cross the boundary, and energy can cross the boundary. So isolated systems completely cut off. What's the most realistic? Like, we see this all the time. What's probably the most likely one? Yeah, open system, right? We've got a boundary, we have our system, and then we have sort of this ability for mass and energy. Now for calculations, a lot of times for experimentation, we focus on closed systems. What that at least lets us do is make that mass cannot transfer, but energy can. And that allows us to sort of, to again, do some very specific calculations. We also introduced a concept of a very useful type of matter to study. This was an ideal gas. Now, just remember the equation that we talk about for an ideal gas. There's a special equation, yeah, PV equals nRT, the ideal gas law. This allows us to relate how pressure, volume, the number of moles of something, and its temperature can sort of be construed or sort of measured. This is nice because everything that is considered an ideal gas obeys this. It doesn't have to be a specific gas, right? It's just that these parameters transcend the type of matter that we're dealing with. All right. So we started talking about this component. We've introduced this concept. Now remember, there was one other piece about it too. This is what's known as an equation of state. Just remember what a state function was. If I had to define what made a state function special, what was it about that mattered? Describes a state at equilibrium, that's right. So this equation can be used to describe a system while it is in equilibrium. Means that there's no changes in pressure happening. There's nothing going on. It is at rest, affect that. Yeah, the other point too, remember state variables are ways of describing a system. These can be things like temperature, the density, the mass, the volume. It's a property or a measurement we can apply to a system that does not matter how that property was obtained. So again, let's say the glass I have here, it has a certain volume. You don't need to know if I filled up this glass by overfilling and then drinking some, or just filled it to this level. How this amount of liquid got into here doesn't affect how much there is. In other words, if I said, get a glass and fill it with 20 milliliters of water, all you need to know is 20 mils of water. You don't need to know that if you overfill it, then pour some out. The path, how we arrive there, has nothing to do with the value, what it is, its temperature, its volume, right? So we separate those two pieces on it too. So we have this dialogue now. We have a common language we can help to describe it. What we're going to talk about today is changing states. We say we start at some state that is defined by an equation that talks about this state. In this case, PV equals nRT. It's the ideal gas law. Now what we're going to do is change the state. We have a system that is described by this equation, and we're going to create a new state by adding or subtracting energy, right? So we're going to move energy across the boundary, and we're going to arrive at a new state. Now, those are going to have new state variables, right? We're going to have a new pressure, a new volume, possibly new nRT. We already said that one way we can simplify this equation, if we're dealing specifically with closed systems, which of these variables, P, V, N, RT, will be constant in a closed system? Number of moles, right? R will always be constant. It's a universal gas constant. The number of moles stays constant because we're saying the mass cannot transfer. So we've now knocked it down where there's really only 3. Of the 5, there's only 3 that we're going to play with. P, V, and T, right? Pressure, volume, temperature. So based on this, if we have a closed system of an ideal gas at constant temperature, what has to happen to the volume if you double the pressure? Doop, doop, doop. So take another couple of seconds. Again, if you see the poll on your screen, just click that part in. All right. Give another 5 seconds. And time. All right. So we got distribution. I would agree D. Majority rules here. D is the correct answer here. So let's work through each of these. So first off, by elimination, how can we eliminate E, for example? What is the information as given is something that we can say, no, you know what? E we can actually deal with. E is not true. There is actually enough information here. Yeah, it's a relationship, right? P equals nRT. We've got something that tells how these different values will change. So E's off the table. Okay, does not change. All right, so if we were to change the pressure, how would that be possible if somehow, what happens to the volume if we double the pressure? How could the volume not change? Think back to the overall equation. I put up the equation here, P equals nRT. We're saying R must be constant. It's not going to change because that is a gas law. We said, why would N be constant? What is the information that's given in this system that allows us to say, you know what? Yeah, we said this is a closed system. So that means that there is the delta N must be equal to 0. There's no change in N. So if we are we said the pressure here is doubling. We're increasing that pressure. If this is an equality, right? If this is equal to each other, how could this volume, just again, hypothetically, let's not look back at the question. Hypothetically, how could volume not change? How could I make this so delta V equals 0? If I really wanted to make delta V equals 0, exactly. If you look at this and you're like, okay, I am definitely changing my pressure. I'm increasing it. And if this equality is going to hold, if this equation is going to hold, something else has to give, right? If the left-hand side and the right-hand side are going to equal to each other, and I'm saying that no, the delta volume is going to be equal to 0, then something over here has to also increase in order to compensate for that change in pressure. We said it's closed, so N is 0, R is not changing. Temperature is your last handle that could potentially change if the volume wasn't going to change. Right, but that's not the case. How do we know? What's the other information given in this system where we know delta T must be equal to 0? What information does it tell us? Yeah, this is going to be done at constant temperature. Constant temperature just means T final must equal T initial. Right, that's the first value. Okay, so we've eliminated E, we've eliminated A, and now what we've got is values. So doubled, quadrupled, or decreased by half. So even just based on quantity, if you look at the two things, so what we're focusing on, if I have to say this, right? Delta N is 0, Delta R is 0, delta T is 0. Another way to write this is PV equals 0, right? If PV equals 0, the other way I could define that is P must equal to 1 over V. Yeah, they are inversely proportional. In other words, if one goes up, the other one has to go down, right? So even based on that, forget about knowing the quantity, look at those three values that are left. Doubled, quadrupled, well, those are increasing. Decreased by half, that's the only one that goes down. So we've already eliminated D. Even if we didn't look at the magnitude, D is the only example that can go down, right? No, delta, sorry, not PV equals 1. What I mean is, think of it this way. Delta PV must equal to 0. The product of the change between pressure and volume, P1 V1 must equal P2 V2, right? That the equality must be held. The reason why is the change in N is 0, the change in R is 0, the change in T is 0. Therefore, the change in pressure volume, delta PV, must also be equal to 0. Okay? So that way, this equality holds here. The other way to write this would be, yeah, P1 V1 must equal to P2 V2. Somehow the product of these twos have to balance out. And that's where you can say that, look, if the delta P is equal to 2, the delta V must equal to 1 over 2, 1/2. Okay? But again, you can do this also by sort of rationalization, looking through each of the questions and breaking down. So it's decreased by half. Okay, let's try one other one. Closed system, ideal gas. What happens to the temperature if you double volume? Whoops. Let me relaunch that. There you go. New poll. Same kind of idea. All right, 5 more seconds. And all right, time. So what we get for that one, B is coming up as the popular answer. So once again, let's apply the same logic we just did in that first example. We have a case, P equals nRT. What are the things that are not changing? What can I say? The delta what must be 0? Okay, so we know it is closed. Delta N equals 0. It's a universal gas constant. Delta R is equal to 0. What else? How do we know delta P is equal to 0? What's the wording on that one? Constant pressure. That's right. Delta P is equal to 0. So the only two handles we have are volume and temperature. Notice they're on opposite sides of the equation. What we're saying is the change in volume must equal to the change in temperature. In other words, they're proportional. They're directly proportional. Doubling one must double the other, right? So that's how we know this. Now again, how would that first example, if A was going to be the case, what must happen if I really, really want to double the volume? How could temperature not move? What must be true for temperature not to move? Yeah, P has to go down. If I'm saying temperature has to be held at 0, this is the guy that's got to give. Remember, we've only got 3 degrees of freedom, right? If we're saying it's closed, N and R are locked in. We have 3 different sort of degrees of freedom, and we have to push and pull between the two these different parts, right? So in this example, yeah, it's going to be doubled. What if I modified the question just slightly? What if this was a closed system, ideal gas, and I changed the temperature? And that's all the information I gave you. Closed system, ideal gas, and I changed the temperature. What might happen to volume? Can I, just with that part, closed system, ideal gas, change temperature, is that enough information to know exactly what must happen? No, because remember, I have 3 degrees of freedom. I need to lock down one of those 3. Closed system, okay, remember, you've got 5, right? R, off the table, gas constant. Now we're down to 4. Closed, okay, N's off the table. Now we're down to 3. I need to lock off one more of those in order to be absolutely sure what will happen, because it does have these different components. And this is one of the examples we talked about last time. This is a way we can use this kind of a system, an ideal gas, where we can actually move energy as heat and temperature does not change. So remember, what was the other example we talked about last time? What is a system we discussed last class where I can put energy in and there's no change in temperature? What was the example we used? It was something, yeah, phase changes. That's right. Solid block of ice can warm up to its phase change temperature. Adding more heat causes the phase change, but does not change the temperature of the system, as long as the system is made up of the liquid and the solid component. Here's another way that we can actually put energy into a system. Let's say I added heat, but if this was where the delta T was 0, right? Let's go back to this one over here. If I said for some system where PV equals nRT, well, if I'm going to say it's closed, so delta N equals 0, we've already said R, delta R equals 0, and if it is, I really, really want to make sure there's no change in temperature equals 0. I have 2 degrees of freedom. I can still do this. I'm not breaking any physical laws, which means ideal gases can undergo a change where we have P1, V1 turning into P2, V2. As long as delta T is set to 0, I've got 2 degrees of freedom. Pressure and volume can play with each other. I can add heat or take away heat to this ideal gas, and there will be no change in temperature. There's just changes in pressure volume. These are the manifestations of what these look like. And we're going to jump into this one as we start to talk about the first law of thermodynamics. This is why we start playing around with ideal gases, because they are useful constructs. Yes, this has to be a closed system. You're right. This is a closed system. That's why we're saying right here, delta N is equal to 0, right? We have to make that other assumption. So we actually, there's a couple layers. Saying that it is an ideal gas has another sort of consequence too, right? Remember, if I say it's an ideal gas, what am I really, I'm locking up one more parameter. Which one is that? Yeah, R, or the fact that, remember, we can use the ideal gas law to describe it, right? Ideal gas says PV equals nRT is on the table and R is constant. Closed system, N is constant. Then we have what's called no temperature change, no pressure change, and no volume change. Does anyone know the name, the special word that we apply to a change that is happening where the temperature does not change? There's a name that we use to describe that kind of change or that kind of process. Yeah, isothermal. Isothermic. The name isothermal describes the change in, or something changing where iso, the same temperature. The change happens with no change in temperature, so that's another way of describing that we're talking about delta T equals 0 for a process. So, again, using the ideal gas law is a useful construct to talk about a system that we can sort of behave and we can use. What we're going to talk about now is the first law of thermodynamics, and it goes back to this concept. We're talking about pushing and pulling energy, and all we're really doing is if I put in pressure under the construct we said, delta T is 0, delta N is 0, delta R is 0. If I put in pressure, I get out volume, and vice versa, right? They act equal and opposite against each other. What we're saying there, that is a statement of conservation of energy. This is the first law of thermodynamics. We're saying that if energy in a system is there, it can go somewhere else or we can add to it. System plus surroundings must equal universe. We're saying that energy cannot be created nor destroyed. It can change where it is, it can change how it is organized, but it doesn't go away. That's kind of the concept, or the really, really distilled down version of the first law of thermodynamics. We're saying that energy is this constant as long as we look at the overall universe, right? The total energy of the universe is constant. We can just move it from within the system out to the surroundings, or from the surroundings back into the system. Now, in terms of sort of, especially ideal gases, we're going to define this state variable, just like a temperature, a density, as the internal energy. The internal energy usually gets a term, U or E. The internal energy, this concept, this measured value, is really a sum of all of the energy inside the system. And you put it all in a big bucket. We're saying that, okay, for my system, my glass of water here, the internal energy is the entire sum of all the translational, rotational, vibrational, intramolecular, electronic energies, everything to do with what's going on in the system. That includes things like bonds. So it's everything, the chemical makeup of this energy. We bin it all together because what we're saying is energy can change which one of these pots it's in, but the total energy is not something that's going to change. So as a quick thing, if you read down this list, does anybody know which one of those terms is totally alien to you? Translational, what does that mean? A translational energy is talking about what? If you had to sort of describe it. Yeah, energy moving left to right. So if I have a particle, here's my amazing particle, if it has translational energy, we're saying it has movement. It's just moving from place to place. We're not talking about anything about its changing, nothing in the internal structure, not about bumping into other things. This is just movement. What is rotational energy? Whoop, whoop, right? Spinning. Vibrational, what's that? Burr. Yeah, molecule goes burr. It's difficult to do with a pen. I don't know if it works like this. Look, ooh, look, it's vibrating. Definitely not as good as in person. Vibrational energy is actually in the bonds, right? It's how atoms in their actual bonding arrangement, they're not breaking the bonds, but they're vibrating. All three of those first things really have to do with another property you're used to sort of measuring. Translational, rotational, vibrational energy. This is kind of a binning. We call it something else. Starts with a T. It's another way of measuring a state in a system. Usually that's what? The total kinetic energy associated with, translational, rotational, vibrational are usually associated with the concept of temperature. It's motion of the molecules and either rotating, vibrating, or moving around, right? So at higher temperatures, it just means we've got higher translational, rotational, vibrational energy in the system. The last two, intramolecular energies and electronic states, what does that kind of sound like? Intermolecular is what? Inside molecule or between molecules? Yeah, it's between, right? It's how molecules like to connect or sort of attract to each other. Electronic energies, does anybody know, as heads you guess, what would that be? It's like ionic, right? You can think of it as charges holding on to each other. It can sort of be binned also as bonding energy too. What that means is that's kind of like potential, right? If we have something at really high temperature, it's going to have a lot of translational energy moving around. If we cool it down, that translational energy gets sort of binned in to intermolecular interactions. Molecules get closer, they hang on to each other. The energy hasn't changed, they're not gone, they're just changing state. So it's kinetic and potential energy all built in together, yeah. So it's kind of the same idea as kinetic and potential, which you do in physical. So, but the point is, anything, if it's a molecule, if it's a balloon, we can sort of sum it up that the total internal energy is given by the sum of all of these different pieces, the kinetic and chemical potentials in the actual system. So, now that we've got this concept, what we're going to say is we're going to start with a system at some state. We're going to then change the system and create a final state. Remember, there's a definition we like to we have to put on this. If the system is at some initial state, the system is at some final state, we're making an assumption about those states. It starts and ends at what? They end and start at, starts with an E, equilibrium. We say that everything is cool and chilling out, there is no net change, then we induce a change, and then we watch it until there's an end again. In between, the change between those, that is our process. That is our path, right? That's how we get between these two states. So we can imagine the way you can do this is you can describe, we have well-defined equations that describe the initial state because it's at equilibrium, There's a change, stuff happens in between, and then we have our final. The reason I do this is because the process can be messy. The process could really, really be different. How you get between two different places is what's known as the path. The path variables, or how we go between them, those do change. Those are something that do matter, and those are something that can actually, that can affect sort of a process, what we sort of learn from it. But the first concept we want to do is that this change, a state to a state, is a really valuable quantity for two reasons. One, it tells us about those two states, any two states. Since I start here, let's say coffee at 75 C and coffee at 25 C, all I have to do is know where I start, where I end up, and I can define what that difference is by measuring how much energy left the system, for example, how much heat had to be dissipated, or whatever. Something had to happen to get between these two. And why this matters is 75 C, that is a state, which means I don't care how I got to 75 C. I could heat it up to 100 and let it cool to 75. I could carefully heat it to 75, but everybody could agree, look, if I want to measure the difference between these two, get to 75, hold it at equilibrium, then let it come back to 25, hold it at equilibrium, measure what happens in between the two, and everybody agrees that yes, final minus initial equals this delta, the change between the two. So for any of these systems, what we can say is the total internal energy can change between these two. And the reason we use that is, okay, right now, how much internal energy is in this water? That is not an easy quantity to come up to. It's very difficult to take a point quantity and say, quantify this, measure this. We don't have a probe that says, what's the total translational? We can measure the temperature, maybe the density, bits and pieces of this. But it's really difficult to describe absolutes. It's very easy to describe differences. If I measure where I start and where I end up, the difference between the two is something I can put a measured value on. So if I was going to say how much internal energy is in this system if I start at 60 and drop to 10, that difference in temperature I can measure by how much heat left the system as that process happens. This is why we focus on these difference values. They're easy to do measurements on, and we have a reference state between those two. So what we're going to say is all of our systems for thermodynamics, the systems are going to be perturbed by moving energy, not matter, meaning we're dealing with closed systems primarily, right? Two, there are two ways, two different currencies of energy we can use. Heat is one we've talked about a lot. The second concept is work. So heat and work are my only two handles that I can use to change the energy inside a system. So heat, we've already talked about, that's a direct, transmission of energy that usually we think about it in terms of the kinetic parameters. It's kind of associated with something like temperature, or at least in your mind there's a link. Remember, we will break that part down. Heat usually has a value of joules. Work also has a value of joules, right? Energy is just energy, right? We're saying that energy total can come in these two different flavors, or these two different values. Means we can affect a system by only using heat, I can affect a system by only using work, or I could use some combination of the two. This is why thermodynamics comes in, because remember, we talked about heat and movement, or heat and change. Thermodynamics, do you know what industry actually really gave birth to this major focus on thermodynamics? What was the thing why did we create this? So we could do something better. Does anybody have any recollection of where this comes? Yeah, coolers, right? That's one. So things like, cooling things down, heating things up. It really had to do with motion, locomotives, engines, right? So this is where what we're trying to do is figure out, how do I take chemical energy and turn it into physical energy? How do I burn something and then move with it? Or how do I take movement and turn it into something else? So it's this interconversion between physical properties and energetic properties like electricity and, heat, really, right? So it's that piece that really comes down. So we define the world in these two packages, work being the thing we usually want, and heat, the thing we usually add to a system. Now, the first law of thermodynamics is the statement of conservation of energy. We're saying that the delta E for any system is going to be equal to the Q plus the W, the heat plus the work. So what we're saying is, remember, first thing we said, all the energy in the universe. None of it goes away, none of it's destroyed. If it starts in the system and it leaves, it must go to the surroundings. If it starts in the surroundings and comes in, then it means it's leaving the surroundings, coming into the system. But the difference is something we can measure. And more importantly, all energy, if a system loses energy, it's either going to lose it as all heat, all work, or a combination of the two. But summing those two values, heat and work, allows us to measure those two properties. So we've got these two basic ideas. Energy is either heat and work, so it's a sum of the two. And the difference, final minus initial, gives us the delta between them if we're studying a system, right? If I look at a system and I could see this difference between it, I can now measure that delta E value. So it's a very useful concept. It allows us to actually sit there and measure what happens to a system by sitting at the boundary and watching heat or work change, right? So heat, we're going to talk about this a little bit more next week. This is a concept or an area known as calorimetry. It's a measurement of movement of heat, and that has how it deals with temperature. Work is something you're a little more directly familiar with, right? Work is an energy over a distance. In physics, what do we describe? What's the unit of work? Or what's the equation for typical work in a physics kind of a context? Yeah, Newton meters, right? Energy and distance. Force times distance, right? Force times a distance equals our work value, right? Well, because we're dealing with three-dimensional objects, the typical one we're going to focus on for our work values, right? We're going to deal with three-dimensional things like imagine a balloon that's expanding. We define work as PV, pressure volume. More specifically, it's the negative external pressure multiplied by the change in volume. Now remember, what is the units of pressure? Pressure was usually, what's that ratio? Force over area, right? Quick roll back, is pressure an intensive state variable or an extensive state variable? Yeah, it's an intensive variable. Doesn't matter how big the system is. That's just fun trivia passed out. Yes, pressure is a measure of force over area. Volume is area. Therefore, this is three-dimensional work, right? It's still got that same general idea as force over a distance. We're just talking about a three-dimensional area that's going to be affected by this force and distance. So work is still the same thing. It's a multiplicative product between force and distance. The one thing we're going to do is, remember, work happens when there is a change. So we usually define this as, remember, delta, the work is the change in pressure and change in volume, but we make a definition. We're measuring the change in volume of the system as it expands or contracts against a constant force, where the constant force is what's known as the external pressure. We're saying if I had a balloon in an atmosphere, if I wanted to make it bigger, what happens to delta V? Is delta V positive or negative if I blow the balloon up? Delta V for the system, plus or minus? Yeah, the delta V is plus, right? Because it's going to get bigger. Okay. Now remember, you're putting on your glasses, you're watching the system, right? You're staring at the system. Here's my system, it's the balloon. It gets bigger. Okay, so delta V is plus. What about work? This system, is it expending energy? Is it doing work? Does it have to push things back as it gets bigger? As it fights for more area, what is it doing? It's doing work, right? It is using up its internal resources to push the thing back. The thing it's pushing back, constant all around it, is the atmosphere. That's the external pressure. That does not change. This balloon getting bigger doesn't suddenly change the pressure of the atmosphere. That stays the same. So we say P external is constant. That's one part. Now look at that too. If delta V is plus, what is the sign of work based on this equation? Delta V is positive, P external is just a value. Sign of work must be minus, negative. Okay, does that make sense? What are we saying with that? A balloon got bigger. Did the system lose work or gain work as the balloon got bigger? Yeah, it is negative. What we're saying is the system had energy. Boom. It is going to do work. It is pushing the atmosphere back. That happened because of a positive delta V. It had to push the atmosphere back. Okay, as it does that, at the end, it will now have less energy because it had to use up some of that energy to shove the atmosphere back. Work is negative from the perspective of the system. So this is what we're coming into now, is it's all about reference state. Usually, chemistry, we will focus on the system and we're saying what happened to energy with the perspective of the system. In the case of work, since I have to shove the atmosphere back, a positive delta V equals a negative work value. Work is leaving the system as that happens. So watch your language. The sign that we ascribe to heat and work can be figured out based on what we say is happening. If the heat is absorbed by the system, that means it will be a positive value. Heat is entering the system. We could say heat leaves the system, negative. Heat is absorbed by the surroundings. What's the value of heat in that example? Heat is absorbed by the surroundings. Then with respect to the system, it must be negative. Exactly. If the work is done on the system, what does that sound like? Work was done on the system. That means the outside is pushing in. What do you think that the value for delta V for that last example is? If work is done on the system, what would we expect delta V to be? Yeah, that's getting smaller. What would we call that? Compression or expansion? Yeah, that's compression. Delta V goes down. So learn each of these terminologies, right? What we say, compression means a certain sign on delta V. It's a delta V that's negative. If a system does work on the surroundings, it is negative. It is pushing back this overall part. Okay, let's give it a shot. So, yeah, please.
You said that compression, with compression, delta V goes down. But if you're changing like the amount of volume in the system, wouldn't it be a bigger, like wouldn't delta V, like the change in V increase?
Well, no. So if my system starts here, and I said that the surroundings does work on the system, the implication there is that the W must be a positive value, right?
Yeah.
Okay, so that's one. If W is a positive value, based on what we said here, the only way W will be a positive value given an external pressure, constant external pressure, the delta V must be negative. The volume started big, it is compressed, it is now small. Delta V, looking at the system, it was big, it's now small. Final is smaller than initial, right?
Okay, that makes sense. I think I was just thinking in terms of like change in general, not negative or positive.
Right, magnitude is a different part, right? Magnitude totally depends on what values we're talking about, but sign is just a function of where the energy starts and where it's going, right? Any other questions? This is everything. We're putting it in the context of a balloon just because that's an easy sort of system with an ideal gas we can sort of deal with. But anytime the surroundings does work on the system, we're implying that it is a positive value. Done work on means it's happening to this. Now again, we're really going to talk about this in the context of gases because delta V is easy to calculate there because we have a nice constant external pressure. When we get to liquids, it gets a little bit more weird because they're a lot less squishy. Delta V's are harder there. We have to deal with chemical reactions to sort of talk about that more. Okay, so where is this? So, reshare, relaunch the poll. System does work on the surroundings. What is true? Any of the above could be true. That's right. It could be anything. That could be any bowl. All right. And we're going to go time. Yeah, if it doesn't pop up, not a big deal. It may just be hidden behind one of the other windows. All right. So, C is coming up as the big answer. Yeah, I agree with that. What we're saying there, remember, is the surroundings system does work on the surroundings. We're saying that the energy has to leave the system. And again, think of it this way, and when you're doing your exam, if I am a system, I am doing work, I'm pushing out, I'm leaving energy, right? I'm pushing the atmosphere back, so it has to be a negative value. The other thing, too, I want to highlight here is, what does this little thing mean here? W cis. What are we saying when we've got a value, a variable that you've seen before, and then cis below it? Yeah, W is your work. Remember, we've got W, and what's heat? What's the letter we use for describing heat again? Q, that's right. What's energy? Total energy? We have two letters we talk about that. Total energy in the system can be, yeah, U or E, right. So these are the values you should be triggering in now for a thermal. Cis, this little subscript cis is saying it is the work associated with the system. It's putting a perspective on it. So what should the value, if this was work surroundings, what should that value be? If system is negative, surroundings had better be positive. What is that a statement of? If system is negative, surroundings must be positive. We're talking about not equilibrium. Equilibrium means no more change. What's that? If it disappeared somewhere, showed up somewhere, yeah, conservation of energy. It goes from somewhere to somewhere else, right? The energy is not being destroyed, it's just moving around. First law. Okay, so remember, the first law is we apply it right now to our gases. Delta E, the total change for any state, can be measured by heat and work. So let's say we've got this change where we know 50 kilojoules of heat is added to the system, which then turns around and does 10 kilojoules of work. What's the total delta E with respect to the surroundings? Yeah, you can go ahead and either put it into chat, write it out. So we're getting some plus 40s. I got a minus 40. Anybody want to bet for 60? No action on 60. Okay, so we've definitely got 40 sort of circling that point, but there's a question of sign. Yeah, okay, so let's break it down. What is the value? Let me go over to my clicker. Remember, the total delta E is equal to Q plus W. What's the value, first of all, for Q? Value for Q, yeah. At least with respect to what? Heat is added to a system, right? So you're right, heat is going to be 50. But if we are going to be calculating the surroundings, let me write that better. Surroundings. With respect to the surroundings, the heat is added to the system. That means with respect to the surroundings, heat must be negative, right? The system gained it, it's plus 50. Surroundings, it must be negative. And then the system turns around and does 10 kilojoules of work. The system is going to do work on the surroundings. It's going to pick up 10 kilojoules. So overall, with respect to delta E surroundings, negative 40. Okay, so two things. Which is the value? Which is heat? Which is work? Second, what are their sign with respect to whatever you're deciding to measure? In this sort of case, you were measuring with respect to, from the perspective of the surroundings. So all those things apply, being able to transpose between them. Okay, so that's just it. Longhand. We're saying you can think of it diagrammatically like this. You have a system, you have a surroundings, heat goes in, surroundings comes up, and then using a diagram like this can allow you to sum everything from all sort of perspectives. The system will be a value of plus 40, surroundings must be the negative of that, it's the minus 40 value. Okay, so we've broken this out. We've got our initial state, that's remember our state function. Final state, that's where we get to. They both must be at equilibria. We're focusing on this process. So we've talked originally about our state functions, our state variables. These are the measurements of quantities. So these are things like our internal energy. These are things like density, temperature. These are intensive or extensive state variables, right? Now we're going to talk about these path variables. The reason why is because they allow us to define a specific way to get from state 1 to state 2. Heat and work, we've already talked about them. Now we're just going to bracket them in. These are path variables. What I mean there is if I start at some initial state and I tell you how much heat and how much work, I am locking up that process. And once I tell you how much heat and how much work must be involved to get from initial to final, there is only one path now. If I didn't tell you how much heat or work, there's infinite number of ways to go from one to the other. But if I say you must use this much heat and get back this much work, you've now locked it up, because remember, the delta E, that's what we said about the first law, delta E is final minus initial. And we said delta E, at least in terms of these processes we're talking about, the heat plus the work must equal our delta E. Just like our first examples with PV equals nRT. I've got an equation that describes how that change can be quantified. We're defining that change as being due to only energy, heat, and work. And if I tell you how much heat there is and how much work there is, I have locked it up where there's now only one path. I've limited it to one way to go between these two. So without those, we don't know. What this means now is heat and work, because they are these path variables, it means that now we have to think about them, remember, as something that only exists during this change itself. It's not that the system has heat. It doesn't have work. It's not a property of it. It is a quantity of energy that happens because of an exchange. It comes into existence when the energy is moving. It disappears. It doesn't exist anymore, because what we're defining, at least between these... Lucky, come on. I know, it's almost class done. You can go out soon. Okay, Lucky's going to help me in this last part. He is a giant bundle of internal energy. Right now, he's got a lot of potential. He's not moving. When he starts moving, we have a path that's associated with that. He really, really wants to go to the washroom. It's only during that change. Yeah, okay, there we go. Hi, other funny buddies. It's only during this change that we talk about this heat and work. It's during this path that these properties actually come into existence, okay? The reason why, this is partly definition, but remember, they are not state variables. They don't describe a state at equilibrium. They only describe what happens to get from position 1 to position 2, meaning that they are describing that path in between the two. As an example, one day when we get to return to campus, this is where our lectures are normally held, right in the center, next to the bus loop, center part of the chemistry block, center of the entire campus. Let's call this initial state. For anybody else that's seen or walked around campus, does anybody know what that green X is approximately? You know kind of what that is? It's south of 16th, kind of down there on Westbrook. Yeah, but there's something. Yeah, Save On. There you go. It's the grocery store down there. That's our initial and final. Those are state variables, position, descriptors of those two states. At equilibrium, ideally, they are not moving, they are not changing in terms of their position. If we have person 1 and I define a certain path between the two, that is a direct path that will require a certain amount of energy and a certain amount of time, right? Or if you think about it just in terms of thermodynamics, heat and work, you have a defined amount of heat and work that must be expended or taken up by the system to get along that path. If I have a more creative friend, starts at the same initial and has a very different path variable, we have a lot of different energy along that path. Initial and final, the delta E is the same. But what happened on that path, how much heat and work was involved, very, very, very different, okay? Paths can change, initials and finals do not. And this is why we define them as different things. State variables sit, they are irrespective of the path. The path, though, can be described as long as we have enough information about what that path is, okay? So, this is where we're going to kick off today. I'm going to talk just about this idea because we're introducing this concept of a piston. Has anybody known or heard of a piston before? Really good question, Charity. We'll pick that one up right at the end of class. That's a very good thing. Her question was, for people that missed it, how can energy be a state, but then this transition of energy, heat and work, be a path? We'll come back to that one, but it's a really good point. So yeah, a piston is really this. It's in physics, we see it a lot. You think about like a container, three-dimensional container with a lid that can move. That's the important thing. What does that mean about volume? Solid container, lid that can move, volume can vary, right? It means that pressure inside could vary. It means that temperature could vary. Open, closed, isolated. What type of system is this? Yeah, this is a closed system. We define this because if we have a closed system, ideally, what does that mean about N? Closed system, N is constant. Yeah. We've defined a closed system where volume can change, pressure can change, temperature could change, right? This is why we go back to our ideal gas law, because now we have a system where we've got those three things we talked about, the three parameters, and we're not changing N and not changing R. They're ideal gases, ideally inside these. So now we're going to further constrict it. If I keep pressure external constant, right? And now we're going to do something to this. I'm going to add heat to the system. What do you think happens before the animation kicks off? I'm keeping the external pressure constant, but I'm adding heat. What happens to volume? It's going to expand. Yeah, particles may move faster, right? Temperature could get faster. But this is a case where, remember, if what I do is if I increase my volume exactly at the same rate as I add heat, the particles don't have to move faster. They all have more energy, but they also have more playground. So if what I said is, okay, the internal pressure is going to sort of increase in that case, right? The external pressure is constant, but the internal pressure rises. As the internal pressure rises, the volume also gets bigger, right? So as I add heat, what's happening is this compensation is happening. In this way, the average, and I was trying to illustrate with that, this is like that example where if I do this at just the right way, the temperature doesn't have to change because as energy enters, volume is going to be the one that makes it up, right? So I add heat, but volume is the thing that expands, not temperature. Temperature doesn't have to change, right? Okay, so go back. We said heat was something we can add. That's our Q value. What is volume related to? Which of the two energy constants did we say that is related to volume? Heat is our Q, volume is work, right? So if I positive value for heat, what's my value for work based on the example I just showed you here? Plus heat because I'm adding it, but then the volume goes up, work is going to be minus, that's right. And it works out because of this, right? If the delta T for this ideal gas is 0, the heat, positive heat, equals the negative work. It's a perfect balanced system. Every joule of energy I add as heat, if the temperature does not change, will be expended, it'll be converted into work. That is known as isothermal, right? Delta T is equal to 0. What happened here in that awesome animation? This is what? Expansion or contraction? Expansion. In a perfect isothermal expansion, heat equals work, right? So let me write that one down. So we've just defined a case. I've got my piston. It's got some gas inside it. I do my process, and I'm going to add Q, positive value. As that happens, I'm going to go to my final. My delta V is positive, which means work is negative for this overall process. I've got a bigger system, right? More delta V. If this happens, if delta T equals 0, then what's happening here is Q for this process equals W. Or delta E, remember, if delta E equals Q plus W, what does this have to mean about the value for delta E for an isothermal expansion? Yeah, for if delta T equals 0, Q equals W. We're saying there's this interchange between heat and work. We're not using energy to change temperature. As a result of that, for this case, that's the first law, we can rewrite this as 0 equals Q plus W. That's a simplified case where now we can use this as a construct to do a lot of other energy manipulations. The most important thing to hang on, though, is we are adding heat. We are not changing temperature. The heat is being converted in a perfect way into work. The other's true too. If we did an isothermal, so this is an expansion. What if we went the other way? This way is expansion. What would you call this? Let's say this was our initial state. Starts big, goes small. What do you think happens? Yeah, that is going this way is expansion. Going this way we call compression. What's the value for work under compression? Work is plus. That means what does the value for heat have to be if it was an isothermal compression? Yeah, it's negative. They have opposite signs but equal magnitude, but that only happens if we are dealing with delta T equals 0. Okay? All right, this is where we're going to leave off for today. We're going to jump on this and we're going to talk about these different processes in terms of what's known as reversible or irreversible processes in this case. Okay? Review these parts, take a look at the baseline slides. I will see you guys on Friday.